So, how do we do this training? We have been talking about at a very high level the architecture and so on, but we have not spoken about what they really contain, what we feed as input and so on. So, in this I am going to be talking about a typical setup in the translation side, where we are going to be having 3 to 5 million pairs of sentences in the corpora, right. And then a typical corpora, parallel corpora contains about 110 million English words, 116 million French words. In this case, it is going to be English and French. And then the vocabulary size is pretty close to 50K, both source and target. Okay. And then, as I mentioned earlier, the embedded words are fed into the encoder, and then hidden layer could contain 1000 LSTM cells or GRU cells, and then we can have hidden layers from 4 to 8. So, we just saw 1 or 2 layers, right, in the earlier cases. So, we can have more of this. So, we can have 2, 4, same fashion. This is your encoder. Same way you stack them up. Right. So, it is the number of cells are going to be huge there, right. The number of weights are going to increase there too. There are multiple ways of providing the learning rates. So, some will keep it fixed, some will start with a high value to have the learning faster, and then exponentially reduce the value. Okay. So, that is one way of doing. And then we will also have different training models. One is the mini batch. You will find lot of mini batch models in the machine translation. Okay. So, we use a gradient descent using mini batch. We will talk about that in the later slide. The training time, if you use 1 GPU, it is about 7 to 10 days for this set of English and French pairs of sentences. And then evaluation score is obtained using BLOW. We learnt about it earlier, and the scores are usually in the range of 27 to 32. Okay. So, this is what you will find in most of the papers. The values range from 27 to 32. 32 is really good. You remember we had something called adequacy, right. So, what is adequacy? Adequacy is that this is just sufficient for the translation. Okay. If you see a sentence and it is just translating the meaning of the input sentence in some way, that is good enough for me. And later we were also looking at fluency of the sentences, right. So, this one could be a broken English type of translation. This could have some really syntactically formed sentences coming in from the translation as well. So, both are important. If we get to this level, we already have crossed adequacy part, right. So, we want to make sure that we are in this space when the translation happens, and most of the translation in this range have the value of 32 or sometimes 30, sometimes 29 and so on. Okay. All right. So, this is a setup that we have. And then there are certain parameters that we call as hyperparameters, like in terms of what is the mini batch size, the learning parameter size, and so on. And there are parameters that are learned in the training process, like the theta parameter that contains our u, v, and w, and also our alpha now, right? So these are the parameters that are learned during the training process, and we use a mini batch or a stochastic gradient descent algorithms for this. And we require really good machines to do the translation. Okay, so we have a good set of GPUs in your machine. That's very good to start the translation process using neural network. So what are the advantages? I think we saw all of this. So ability to focus on the significant part of the sentence, ability to peek into the source sentence, to really align the target words or the phrases into these source sentences. For all the neural network, when you use LSTM or GRU, you don't have this issue. Okay, and also it depends on how well you taught the input process, right, in terms of providing the input values to the hidden units and so on. Alignments are found automatically. There is no need for you to train this. And the performance of the NMT increases because we are including the alignment process, alignment of phrases into this as part of the training as well. So if you use the vanilla training model where we did not have any of the alignment problem, the performance is a lot lower than some of the statistical machine translation based on phrase based models. So now the attention based models are comparable with the statistical model as well in terms of alignment. Okay. So now we look at different types of different types of NMTs. So here, this is what we saw, right? So there is an encoder, there is a decoder. So for a pair of language pairs, language 1 and language 2. So we're going to be translating from language 1 to language 2. So L1, L2, right? So L1, L3, L1, L4. Suppose if you have about 100 languages and you have the standard encoder, you will have 100 of this, right? So we need to have so many of them. So what had happened is, so when you have the same target language, you don't need to have separate training process for all the language pairs, right? So you can just take one encoder, language 2, language 3, which has the same one because the target is the same, right? The encoding part only is different. And then you can also have a shared encoder. Suppose you want to translate from we can also have a shared encoder if you want to translate from one language to multiple languages. You can have several decoders, okay, but you can have only one encoder, right? So how do we train this process? So the one assumption is you can start feeding this, okay, and then this could be your one batch. For example, if you have about 10 million pairs, you start doing this and then do the mini batch or stochastic gradient descent algorithm and train this, and then don't change anything here, and then use this one, start training this, use this, and then start training this, and then keep doing it until these states are in equilibrium, and then you can start feeding in the input from the decoder side, for you to translate, rather I'm sorry. So, you can feed the input from the encoder and it would translate it for you. So, you need to have some certain kind of mechanism from which language you want to translate into, okay, or from which language you want to translate it into L1. For example, if you have Tamil, Telugu, Malayalam and so on, you want to translate from Tamil to English, Malayalam to English, or from Telugu to English. So, we need to specify or earmark certain tokens so that the encoders know which one you are going to be using. Okay. So, this is one approach where you can at least reduce the number of RNNs, right. So, what next? So, is it possible to have so many of them? For example, there are 100 recognized languages that are available in the world, and if you look at Indian subcontinent, we have 23 languages alone, right. 23 scheduled languages that are available in the Indian constitution, but there are about 100 languages across the world. So, we can't be having so many translation modules in this fashion. Is it possible to have one single module that does the whole job, or is it possible for me to do this? So, let me write this here. For example, I have the translation from English to French, and French to English, and I have let me write Spanish to English, and then Portuguese to English. Let us take this for example, these two pairs. Okay. So, we have learned these two models. Is it possible to do the translation from Spanish to Portuguese without making any changes? That is where some of the researchers worked, and then especially from the Google, they created something called as a zero shot translation. What they have done is they moved away from the sequence to sequence translation. Instead of having those pairs of translation modules, is it possible to have one that helps me in terms of translating into various languages? Okay. So, they are trying to establish a single system that translates between two languages even in the absence of the training corpus for these two languages, like what I had shown, right. So, if I do not have this pairs of sentences, but I have these. So, using this knowledge, can I translate from Spanish to Portuguese is the idea. Okay. So, what happens when we create, you remember we spoke about the interlingua earlier in the beginning of the machine translation, where we want to capture the knowledge related to the source language as an independent knowledge source, and then use it to translate into multiple languages. So, this is exactly they are trying to attempt, even though they claim that it works very well, but the results are still not up to the mark in many cases. Okay. But in essence, their attempt is to create the interlingua. So, they are also trying to see if there is a common representation or a translation knowledge that is possible to create. So, this is their architecture. So, in their encoder they have English. I am taking two Indian languages, Tamil and Telugu. I have English to Telugu, I have English to Tamil translation, and then Tamil to English and Telugu to English. So, this is the box that we are going to be training. So, during the training process, what you do is you just let us say we are going to be doing the training process for Tamil, okay, and then we do this for Telugu, right. I think it is a little messy. Let me erase first. So, from Tamil to English, okay, and then English to Tamil. We train the model, and then take the other pairs, Telugu to English and English to Telugu. So, without changing any of the model parameters, once the training is completed in these pairs, without changing any of the models, start feeding the next one, okay, as pairs. For example, when you are finished with English to Tamil and then Tamil to English, we have certain state in the neural network. Without changing any of these values in the state, start training again. So, the pairs are trained, instead of training only in batches of or in pairs of languages. You finish one pair, second pair, third pair, fourth pair, and do the cycle part of that. Okay. So, use the mini batch or whatever model that you want to use. So, they claim that once this training is completed, they are able to translate from Telugu to Tamil effortlessly. So, this is the attempt that they have made, and they claim that it is working very well in many cases. Okay. So, with this I complete this translation part both in the SMT as well as in the NMT side, and this is the current state of art right now. Okay. And most of the Google translation mechanism, I guess, is using the zero shot model. Okay. So, in the next session, what I will be doing is I will be talking about the beam search. You remember we have been talking about this at the end of every machine translation. Okay. So, here we never spoke about how this is done. Okay. So, we will talk about the beam search, and then later we will talk about the common gradient descent types. So, we will cover these two in the next sessions.